because the definition involves a scalar dot product, we need to understand what it means. Okay, so the motivation of this is we have vectors, right? So we have A, and if I tell you to, let's say I have two vectors A and B like this. If I tell you to add them together, you know how to do that. You just take them head to tail, connect them together, right? And yeah, so you first move this together like this, and yeah, let's make this longer. Let's make the B longer than the A, so we can actually tell the difference when I put it together. So move it just so they start at the same point, and then parallelly maneuver it up here, right? And then connect it like this. Okay, so this is A plus B. And how about A minus B? So I just need to define what minus B is, and it's the same magnitude, but pointing in the opposite direction, and then we can do the same trick. So move A and B together like this. So this is minus B, this is the original A, and then you maneuver them head to tail like this, right? So this is the minus B. So A minus B would be here. So that's the A minus B vector. And then we have scaling, right? So what does 3A mean? If I multiply a scalar to a vector, well, that just means A plus A plus A. So now you just basically take this and stretch it 3 times longer, right? So that's 3A, because you have this A plus A plus A. So essentially it's a stretch. And you can think of 1/3 of A as basically shrinking it by 3 times, because 1/3 of A plus 1/3 of A plus 1/3 of A should equals to A, right? So so what is 1/3 of A? It must be 1/3 of A. So it'd be yeah. So if this is A, right, 1/3 of A must be 1/3 of A. Okay, so we know how to, for vectors, right? We know how to add, we know how to minus, and we know how to scale. How about multiply? So I've mentioned this many times already. If there is 2 ways to multiply, okay, and they are called, so as multiply, there's 2 ways, and it's the one with the scalar dot product, and the notation is this, and the other is a vector cross product, and the notation is with a cross. Now with scalars, so if I do A times B, I can either write nothing, I can either write a dot, I can either write a cross, so the times sign, either of them they all mean the same thing, okay? But in vector, these mean something different, and never write something like this. This does not mean anything, or it means something very advanced. There is it's called outer product, but that's so advanced that we won't even talk about it, right? So don't write something next to each other. It means something completely different. Okay, so so now you know why it's called dot product and cross product. Why is it called scalar? Because this returns you a number. This returns you a vector. Okay, so that's why this is sometimes abbreviated as the vector product, because A cross B, don't say times, it doesn't mean anything. A cross B or A dot B. A cross B gives you a vector, A dot B gives you a scalar. Okay, so nothing, so this is not, but yeah, this is not the magnitude of this, just to be clear. This will give you a brand new vector. There's no relationship, these two are different things, okay? This is more advanced. You will need this at the very end of the course a little bit, but we'll maybe delay that and just teach you, just teach you what is necessary. Sort of, it's a big topic on its own. But yeah, we'll stick with the scalar product first. Okay, so imagine you're back at the table, at the drawing board, and you have arrows, right? And I ask you, can you come up with a sensible way to multiply these? So you're the inventor. You're the inventor of the mathematics of arrow now, right? And I told you, if I ask you to add, if you're the inventor, I think you'll kind of, if I give this problem to 10 people, I think 9 out of 10 people will come up with a sensible way of, hey, if I just add this is a good way of doing addition, right? This is a nice way, and then you will find a lot of use in physics. Ultimately, whether something is a useful way to do it or not is, whether it's a sensible way or not is first, are you allowed to do it? And number 2, is it useful? So you're inventing a brand new theory, so you're always allowed to do it because you're inventing a new thing. And is it useful? It's really the ultimate judgment of whether it will catch on. This rule of doing this operation will catch on or not. Turns out there's two ways that can be classified as multiply or product at least that is useful. So both of them catch on and it has different application. All right, so back to my question. If I want you to multiply them together, right? What sensible way you would come up with? You would go like, I don't know what would be a sensible or a useful way, but I know how numbers multiply, right? Can I extend that definition to arrows, to vectors? Well, okay, so let's see. So 1, 2, 3. I can think of 2 times 3 is 6, right? As a scalar, everyone knows that. So what's going on over here? So I can think of 2 as a vector that goes as a position vector that goes from 0 to 2, and 3 as a position vector that goes from 0 to 3. So what does 2 times 3 means? Well, it just looks like I am taking the magnitude of 2 times the magnitude of 3, right? Because that will give me a vector that is 6 units long. All right, so maybe if they are parallel, let's say C and D, and if I do a dot product, it's sensible to say it's just C times D, okay? All right, that's a good motivation, right? C dot D, if they're parallel, it goes like that. Now, the question is, what if they are perpendicular? So if I have a vector like this, I'll just call it A and B, and they're 90 degrees to each other. Now, we learned from mechanics that X and Y direction are kind of independent. So what is A's contribution in the B direction? Well, if they were like this, so A fully contributes to B, right? They're both pointing in the same direction. Imagine these are forces, right? So they're both pushing in the same direction. So the product force would just be this times this. But here, A does not really enhance or subtract B. It's doing its own thing. So A and B doesn't really contribute to each other. I would probably want a definition so that A dot B, if A is pointing this way and B is pointing this way, to give 0, to tell me how much they contribute to each other. So if they're parallel, they just contribute as a product, like this. And so I'm just saying what would be a sensible way to do this, right? So if I have something opposite to each other, so if A and B this time are anti-parallel, so this is called anti-parallel. So it's parallel, but they're anti, we're pointing in opposite direction. Then A is almost, if these are forces, A is working against B, okay? So I would like to generate a negative number out of that, okay? So I might, if I want to take a dot product of something like this, kind of want to generate a negative number, maybe A times B, like this, okay? So how about if this is at an angle? If A and B are like this, all right, so now let me resolve A in this direction and this direction. So I'll pick the angle that is sandwiched between A and B. And this is called the included angle. So it's because if I say the angle between A and B, you might ask, should I take the large one or the small one? Always the small one. So that's the included angle. So this part is the magnitude of A times cosine theta. And this part is sine. But this part doesn't really contribute to B. So what's the contribution of A to B? So if I ask, how does A affect B? It's only this part, A cosine theta part, affects B. So I should just multiply A cosine theta with B. Okay, so maybe I will have a definition that's like this. Okay. And in fact, that is the definition of a dot product. It might seem a little bit arbitrary to you, but we'll see why that is useful in different types of physics. But first of all, let's address the issue. I resolved A and not B. You might ask, well, no. So how do I know which one to resolve and which one not to resolve? Turns out it's exactly the same because I can repeat the same process. Let me try my best to copy this out, right? So this should be roughly the same, okay? If I resolve B, so along A, so let's say that's my axis, right? So I'm tilting my x-axis to be this way. So this is B, right? So this is now going to be my bx. The included angle is still here. It's still theta included. Right? So this is going to be the magnitude of and something perpendicular. Okay, so this is B. So this is B cosine, right? Cosine theta included. And this is the magnitude of A, right? So if I resolve it that way, then you see B's contribution to A is A times B cosine theta. Okay. This part of B, that is B sine theta, this part is not contributing to A. Okay. So whether I ask A's contribution to B or B's contribution to A, it's the same. It's A B cosine theta. Okay. So in some sense, you will see that A dot B is the same as B dot A. Okay. You might think that's reasonable because 2 times 3 is the same as 3 times 2. So scalars work the same, vectors follow the same rule. All right, that's good. But cross product actually doesn't. A cross B is not the same as B cross A. All right, we're not going to talk about that today, but just as a warning, it's in general. If you flip the operation, it's not true. If A plus B is the same as B plus A, yes, that's true. But just like negative minus, right? A minus B is not the same as B minus A. So you cannot always, when you do operations, you cannot always flip them. And turns out dot product can, but cross product cannot. Okay, so if I look at this definition, let's see if what are the things you need to remember? Let's put it this way, right? The things you need to remember is it's the dot product is defined as AB cosine theta. Okay, I try to give some motivation, and it basically asks the question, what this number gives you is how much does A contribute to B, okay? Or how much does B contribute to A? It's the same thing. Okay, so this is the definition of A dot B, okay? And let's see if it reproduces what we know. So a couple of special case you want to know. Right? A couple of special case is if they are parallel. So if A is parallel to B, in this case, I guess C and D, I called it over there. If they're parallel, what's the included angle? So if A is pointing this way, B is pointing this way, what's the angle between them? 0 degrees, right? So the set angle that is sandwiched between A and B is 0. So A dot B is equals to AB cosine. See what let's just put it as a table to tell, right? So the included angle is 0. So cosine 0 degrees is 0 degrees, right? Cosine 0 degrees is 1, right? So A dot B is just A times B. Okay. And if A is perpendicular to B, let's do the anti-parallel first. So if A is anti-parallel to B, what's the included angle? If A is anti-parallel to B, then the included angle is, well, you can do the top and bottom. This is one of the special case where it's the same. If you have any other case like this, there will be one smaller and one larger. The smaller one is always what we call included angle. Okay, so if it's anti-parallel, then the included angle is 180 degrees. And what's cosine 180 degrees? Plug that in the calculator and realize it's -1. Right? Remember the graph of cosine at 180 degrees is minus. Okay? So it actually reproduces that. I hope I'm giving an early motivation for this definition. And A perpendicular to B, what's the What's the angle? What's the included angle if they're perpendicular, right? Put them together. Included angle is 90 degrees. So these are the three special cases you want to know. And A dot B, because cosine of 90 degrees, again, draw the graph of that, you know that it's 0. Okay, so if they are parallel, it simplifies to A times B. If they're anti-parallel, it's minus AB, minus the magnitude of A times B. So see the importance of having a vector and not having a vector sign. You can write this if you want, but yeah, I don't know about you. I don't want to write so much things. So you want to keep it simple like this. And if they're parallel, if they're perpendicular to each other, then it's 0. Okay, and I think this is the intuition if you want, even if it's not very intuitive. Don't worry too much. Treat it as a rigorous definition like this. Just to right. So these are the three special cases to remember about dot products. And if it's, I'll let you know as well, if you want a little bit more, if A dot B is positive, it kind of means that A is contributing to B. Okay, so these cases, right, if the angle of A is all the way up to 90 degrees, from here to 90 degrees, A dot B is always positive, right? If you look at the cosine graph, up to 180 degrees, right? Up to 90 degrees. So if this is theta, this is cosine theta, 1 minus 1. From 0 degrees to 90 degrees, cosine is decreasing. So as you increase the included angle from 0, if you tilt A, right? If you tilt A all the way up, as you keep tilting this, A is contributing less and less to B, right? Here, if A is this, A is very supportive of B. If you treat these as forces, A is very supportive of B. But as you tilt here, only part of A is supporting B. The other component of A is not really contributing to A. Until you go to 90 degrees is when cosine becomes 0. So A is completely unsupportive of B. If you think of these as forces, like these two forces sort of work together. Here, part of this affects this, and part of this affects this. And sort of AB cosine theta kind of tells you how much. The cosine sort of reduces, as you can see, it reduces from 1. So it went from just the magnitude of A times magnitude of B to just a portion of magnitude of A times magnitude of B. I think that's the best way to gain an intuition about dot product. Again, ultimately, it's not easy to visualize it, but I'm trying my best to give you something to think about, right? Up till here, 90, then A is not contributing to B at all. But now as you keep going, what happens to cosine? Cosine becomes negative, right? So A, there's a part of A, not only, well, there's a part that is, so if A is now all the way to here, right? So that's your included angle. Well, there's a component of A that still doesn't affect B, but there's another component that's opposing B. So that's why it starts to go into the negative regime, right? It gets to negative domain over here, where A is not only not helping B, but it's working against it. And where's the maximum against? When will A be maximally against B? Is when theta is 180 degrees. Then A dot B is completely, A is completely working against B. Okay, so hopefully that gives you an intuition. So if A dot B is positive, it kind of implies, right? So roughly speaking, A contributes to B, and if A dot B is negative, kind of means that A works against B. Okay, so if the intuition still doesn't make any sense to you, just remember these two facts and you're good for it. So one more fact is how do you, in practice, what to do? And turns out it's actually very easy because you're going to use the algebraic view of vectors. Okay, so this is in some sense a geometric view, included angle, just to be sure, right? We're talking about magnitudes and directions. But when we solve problems, we often like to work in components, right? So the algebra view, the algebraic view, or the algebraic representation of vectors in components, it's extremely easy. Let's say A is 1, 2, B is 3, 4. that. If I do A dot B, well, let's first write out what is this, right? So A dot B, remember to make the dot significant so people can read it. Don't just put a small dot, otherwise it might, if people cannot see it, it looks like you're just putting two vectors together and we don't know whether that's a dot product or cross product, right? So what you do is multiply these two and multiply these two. So it's 1 times 3 plus 2 times 4. And that's the answer of this. I'm not going to prove to you why that works. You can look up on the Google to just see why that is true if you're interested. But just yeah, I'll just present it to you as the skill. I think that's the easiest way, just to get the handle on it. Multiply these together, multiplies these together, and add them. Okay, so 1 times 3 is 3. So 3 plus 8, 11. Okay, so that's how you do dot products. It's algebraically. Now you see the benefit of algebra, because otherwise you need to find the magnitude. And this is a positive number. Let's see if it makes sense to what I said over there. It's not one of the special cases, but yeah, let's see. Right, so A is 1, 2. So 1, 2, 3, 4. 1, 2, 3, 4. Right? So 1, 2, A is this vector, and B is 3, 4. 1, 2, 3. 1, 2, 3, 4. Right. So B is this vector. So you see, if I ask you to calculate the use the geometric way to do it, it's a bit annoying. You first have to find the magnitude of A, magnitude of B, and find the cosine. You have to find the angle over here, which is annoying to do, like that, which is difficult. But if you use algebraic view, now you just perform this and it tells you it's 11 and you're done. And it's positive. So according to me, it says A is contributing to B. And you see that they're both pointing in a similar direction, not exactly the same, but in a similar direction. You can sketch it more properly on a graph paper and just confirm this, right? And you will get a positive number. You can tell that they are contributing to each other. Okay, so I'll let you try, right? So what if I have A is 1, 1 and B is 1 minus 1? How would they look? So 1, right? So 1, 1 is 45 degrees this way. 1 minus 1 is 45 degrees this way. 45, 45, right? So they are now at right angles to each other. So I'll leave it as an exercise to you to quickly check, right? If you do this dot product, do you get a 0? Okay, and you can choose one more where let's say C is, I want it to be opposite of this. Okay, let's make it actually even longer, right? So let's say it's -2 and -2. So can you do A dot B and also A dot C? Okay, and if you do that, you should find that it's just the magnitude of, so I would expect A dot C to be negative if you use this algebraic method to be minus the magnitude of A and minus the magnitude of C. Okay, I'll tell you the magnitude of this, use Pythagoras theorem, √2, magnitude of this is 2 √2, like this. All right, so magnitude of A times magnitude of C is 2 √2 times √2, right? So it's 2 times 2, so it should be -4. And see, if you do the algebraic view, you also get this. So I'm not going to prove to you why this magical way of doing it is the same as the cosine way, but that's all you need really for this. So this is a quick intro to what scalar dot product is. We'll see how that affects forces.